Extrusion is a high-pressure compression process. We force a solid block of metal through a specific opening, a die, producing a continuous, uniform shape. The objective is to apply enough pressure that the solid metal begins to flow like a highly viscous fluid, allowing us to generate massive lengths of complex cross-sections. Managing this pressure is a high-stakes engineering problem. If the required force is underestimated, the machine stalls against the solid billet. If it is overestimated, the resulting stress can destroy the hardened steel tooling. We define the mechanical power required to run the process as power equals force times velocity. Since velocity is a fixed production target, predicting the required force becomes the central challenge. Accurately calculating that force requires us to look past theoretical physics and build a model that accounts for the physical resistance of real materials. The landscape of metal forming is divided by the physical relationship between a material's volume and its surface area. Processes like bending and shearing fall under sheet metal working, while bulk deformation describes processes where we force massive changes in the overall volume and shape of the work part. Extrusion is a primary branch of bulk deformation, specialized for creating long, structural components. Aluminum is the commercial standard for this process, as its crystalline structure allows it to yield and flow predictably under these massive loads. Successfully executing an extrusion depends on how thermal states, friction, and geometry continuously alter the metal's internal behavior. To calculate required force, we model perfectly frictionless plastic deformation, where metal deforms uniformly. In reality, as metal hits the converging die angle, internal flow lines aggressively tangle and shear. The material consumes extra energy to overcome this internal resistance. Engineers account for this extra work by using an actual strain equation that adjusts for these internal shearing forces. This calculation relies on two empirical constants, A and B, which are derived from the specific physical angle of the die being used. Calculating this internal strain is only the first step. The machine's own container imposes an even larger mechanical penalty. The single largest physical obstacle is container friction. In direct extrusion, pushing the billet against stationary walls generates massive friction, adding a pressure penalty proportional to the remaining length. We eliminate this by inverting the movement. In indirect extrusion, the billet stays stationary while we push the die into the metal. Because the billet never slides against the container walls, the pressure equation sheds the friction tax entirely. However, this method requires a hollow ram for the extruded part to exit through. This presents a structural problem. A hollow ram is far less rigid than a solid one. This makes machine design a strict compromise. Engineers either accept massive frictional power loss or sacrifice the equipment's structural stability. Even in an optimized machine, geometric complexity alters the required pressure. Extruding a finned profile requires significantly more force than a simple circle of the same area. Complex shapes have a much larger perimeter rubbing against the die face, spiking the friction and the required force. When geometric complexity pushes the force requirements beyond the machine's limits, engineers must alter the physical state of the metal. This is the role of hot extrusion, where the billet is heated past its recrystallization temperature before it enters the press. This thermal shift radically reduces the material's flow stress, allowing for extreme size reductions that would otherwise stall the machine. But high heat comes with costs. The metal suffers from surface oxidation, and we lose the tight dimensional tolerances achievable in cold working. To manage these extremes, operators use molten glass as both a lubricant and a thermal insulator to protect the die. A cold alternative is hydrostatic extrusion, which uses pressurized fluid to surround the billet and eliminate container friction without the need for high heat. Predicting the required force ultimately depends on balancing geometry, heat, and die lubrication. If the temperature, speed, or die angles move outside of our predicted windows, the physics of the metal react immediately, resulting in severe material defects. The most common internal failure is center burst, or arrowhead fracture. When die angles are too steep or reductions too low, internal flow lines pull apart, creating hollow fractures in the metal's core that are invisible from the outside. A different failure occurs at the rear of the work part, known as piping. At the end of the stroke, the flow changes, forming a sinkhole at the back of the billet. This vortex drags surface oxides and impurities deep into the structural center of the part. Engineers prevent this using an undersized dummy block, which pinches off the metal's outer layer, keeping surface impurities from entering the internal flow. Finally, if the RAM moves too fast, we encounter surface cracking. High RAM speeds generate heat faster than the metal can conduct it away. This rapid thermal spike causes the outer skin of the part to literally tear open as it exits the die. Extrusion is a problem of calculated optimization. A raw billet only becomes a reliable structural component when the mathematical model correctly predicts the interplay of heat, geometry, and mechanical pressure.